Okay, good afternoon, everyone. Let's continue with our discussion of semiconductor fundamentals. And then I'll finish up those slides, and then I'll get into the homework problem, okay? So, all right, so we stopped right here, and I was going over the notations, right? So Ni stands for the number of intrinsic carriers. N is also used for number of electrons, meaning the negative charges, and P is used for the number of holes, number of positive charges. You could have N-type material and you can have P-type material. So the subscript is used to note what type of material or what type of semiconductor it is. So if the subscript is N, then it's an N-type material. If the subscript is P, then it is a P-type semiconductor. Okay. And then again, as I said, N is used to note the number of electrons. And actually, this is incorrect. P is used to note the number of holes or the positive charges. And the subscript is used for type of semiconductor. Okay. So if it's an N-type semiconductor, what does it have an excess of? What kind of charge carriers are available in excess? Electrons. So if you have electrons in an N-type material, are there holes present? Yes. But the number of electrons is much, much larger than the number of holes. So they are in the majority. So the charge carriers. Okay, something happened. Hold on. Okay. All right. So if you have an excess of one type of carrier, meaning they are not, the quantity is not balanced, then those are in the majority. Hence, those are known as the majority carriers. So you have majority carriers. And minority carriers. N-type material, electrons are the majority, holes are the minority. And in a P-type material, holes are the majority carriers and electrons are the minority. So electrons, holes, electrons. Okay, and then we talked about Nd and Na. Okay, now all of these have units of either atoms or electrons or holes per centimeter cube. Okay, and I believe I stated this too. Every time you make a calculation or you perform any sort of calculation, you want to convert those unit prefixes. If it's centimeters, you got to convert it correctly to meters. If it's microns, convert correctly to meters before you perform your calculation. Otherwise, your answers turn out to be incorrect. Okay. All right. So having said that, let's go into the next slide. All right. So carrier concentrations when you have a doped material. These are the equations for the carrier concentrations in a doped material. Now, N-type material, you see these are electrons, and these are the donor atoms. So Nd plus, because they donated an electron, they have an extra positive charge. So the black dots that you see, are basically the charge carriers, and the tiny squares are basically the atoms. Okay, so you have electrons and you have Nd plus in there. And here on this side, you have holes, and you have acceptor atoms or ionized acceptor atoms, which are negatively charged. Okay, so excess of holes on one side, excess of electrons on the other side. Okay, the intrinsic concentration of the charge carriers, meaning the holes and the electrons, will remain the same on both sides. But when you introduce extra carriers, let's say we talk about the N-type material for now. The excess carriers in here in the N-type material is electrons. The electrons are coming from the donor atoms. So the number of electrons will be approximately equal to the number of donor atoms. But the total electrons will actually be the extrinsic electrons plus the intrinsically generated electrons. Okay, but because the donor atoms are large in number, they overpower the number of the intrinsic electrons. Okay, and that's why we can state that the number of electrons in an N-type material is approximately equal to the donor atoms. Okay, compared to the number of donor atoms, the intrinsically generated electrons are very few in number. Same thing happens on the P side. So on the P-type semiconductor, the number of holes, the total number of holes comprise of the extrinsic plus the intrinsically generated holes. But because the dopant or the dopant impurity is large in number compared to the intrinsic number of holes, we can say that the total number of holes is approximately equal to the number of acceptor atoms. All right. Does that make sense? All right. Let's take a pause. Let me know if you have any questions. These black dots are electrons, and these circles are holes. No, there's one circle here just to note that the number of holes is far less than the number of electrons. So it's a good question. The question being asked is what are the dots and what are the circles? So the dots are electrons, and the holes on the P side are so actually holes on both sides are basically hole. Circles on both sides are the positively charged holes, and the dots on both sides are negatively charged electrons. Okay, if you'll see in the N side, you have one circle right here, just to indicate that the number of holes is far less, and there's one dot on the P side indicating just electrons are far less. Yes, you had a question? Okay, all right. Okay, so a very curious thing happens when you introduce dopant atoms in there, okay? Actually, you know what? Let's continue with the slides and then I'll come and talk because that is also associated with the homework problem. So let's go through everything and then I'll come back. Just want to make sure all the slides are in. Yeah, okay. All right. And so since there are very few holes, this equation right here can approximately describe the number of holes on the N-type material, and this equation can describe the number of electrons in a P-type material. Okay, it's very similar to the equation that we saw earlier for the intrinsically generated charge carriers. Okay. Now, all along, keep in mind that no matter how many dopant atoms we introduce in any kind of semiconductor, the overall charge will always remain neutral. Okay, the overall charge will always remain neutral. So that piece of semiconductor material, even if it's N-type or P-type, it is just indicating the number, the quantity of charge carriers. It's not indicating the actual charge. The actual charge is still electrically neutral. So I'm going to come back to this later, okay? So acceptor atoms and the donor atoms, they're both ionized because the donor atoms are donating an electron, so they have one extra positive charge, and the acceptor atoms are receiving or accepting an electron, so they have an extra negative charge. So they're ionized. And acceptor atoms, thus we say that they create holes or positive charges. And donor atoms, of course, they're donating electrons. Hence, we say that they're creating electrons, meaning an n-type material. Now, we say in an n-type material, there's an excess of electrons, very few holes. But it does not mean that the acceptor or donor atoms are completely zero in either one of those materials. Okay, so if you have a n-type material, obviously we are doping with column 5 element. So they're all donor atoms. So that number is not going to be equal to 0. At the same time, it is possible that we have a slight dopant from an acceptor impurity. Okay, so that is also possible where Na is not equal to 0. It could be intentional. It could also be unintentional sometimes. Okay, it's never possible to get 100% pure material. Just not possible, right? Ideally, we would like to state that, but real life, it's not possible. Yes. Purity wise, silicon purity while fabrication can be about 99.99 or even higher than that. Same thing with the gases that we use during fabrication. Purity is like 99.99 something, 999 or something. So typically it's counted in parts per million. So very, very low, but it's still present. Yes. Sorry, let me repeat. So the question being asked was how pure can a material get, or what is considered pure? And so typical ballpark numbers are 99.99 or 99.999. Okay, go ahead. So I will talk about that just a little bit. Yeah, yeah. So in an N, were there any other questions? Okay, so in an N-type material, it's not necessary. We have donor atoms, so we have Nd, number of donor atoms, but it's not necessary that there are no acceptor atoms. Okay, so Na and Nd would not necessarily be 0 in either one of those materials. But the criteria would be that in an N-type material, the number of donor atoms would be far, far larger or greater than Na. Okay, and I would typically indicate this with another symbol of being greater. So it's far, far larger than Na. So it's Nd minus Na would give you the total number of electrons. And same thing happens in a P-type material. P-type material, we dope it with acceptor atoms. And so Nd technically would be 0, but in real life, not possible. Okay, that could be intentional or it could be unintentional. So Na and Nd are not 0 in either one of those materials. In a P-type material, obviously we want more positive charges, so the number of acceptor atoms be far, far greater than the number of donor atoms. Okay, so that's the point I made earlier. The number of electrons would be approximately equal to the difference. And here, the number of holes would be approximately equal to the difference. Okay. So far, so good. All right. Then there was a question about compensated semiconductor. So compensated semiconductor is where the doping profiles of both kinds are almost the same. Okay, almost the same. So we designed it for Na and Nd to be almost equal. And so that is known as a compensated semiconductor. It behaves like an intrinsic material. So you have an excess of holes on one side, excess of electrons right around it. Okay, so in the same semiconductor material, you'd have an excess of negative charges and positive charges. So that is what is known as a compensated semiconductor. It's like an intrinsic semiconductor, but the quantity of charge carriers is now very high. Okay, and of course, that begs the question of why would we do that? What's the difference? Well, here's the critical thing. Intrinsic semiconductors by themselves, as we stated earlier, are not very useful, right? We cannot use them as an insulator. We cannot use them as a conductor. But now, if we introduce more charge carriers in there, those charge carriers, because of the number of quantity that they are present, we can actually control their movement with externally applied electric fields. So it's all about controlling the device in a way that works for our application. Okay. So again, compensated semiconductor would be very similar to an intrinsic because the charges are balanced, but those charges are intentionally introduced in there so we can control it. Typically, these kind of devices would be very low conductivity, so we can create some resistors using these kind of doping profiles. Right, so that's basically compensated semiconductor. That's one of the applications. Okay. All right. So what consists or what is considered as a good doping number? We saw that the intrinsically generated carriers are typically around 10 raised to 10, right? 1 into e raised to 10 atoms per centimeter cube. So intrinsic concentration, and this is at 400 K, but at 300 K, it'll be somewhere down here in silicon. Okay. So the lowest is pretty much 10 raised to 14. 10 raised to 14 atoms in a semiconductor material per centimeter cube would be enough to be higher than the intrinsically generated charge carriers. Okay. Typical dosage ranges from 10 raised to 16 to 10 raised to 18. And then depending on your application, you might be a little bit lower or you might be a little bit higher. All of these calculations, all of the processes, again, that's a separate course by itself. It's a separate separate field of study. And as for example, if you want to create a resistor in our silicon material, we'd create or calculate the dimensions. From those dimensions, depending on what kind of resistance we want, we can calculate the dosage, meaning the number of atoms we want to implant into our semiconductor material. Okay, so in general, 10 raised to 16 to 10 raised to 18 is at least what I have seen and what I have read. Okay. As you introduce more and more and more charge carriers in there, what happens? What kind of material has a lot of free electrons? Conductor or metal. So if you dope your semiconductor something about 10 raised to 21 atoms per centimeter cube, it acquires near metallic properties. Okay, because there are plenty of electrons available for conduction, and because there are plenty of electrons available for conduction, it starts behaving like a metallic conductor. So this gives you, excuse me, this line or graph gives you an idea of what kind of doping profiles are used in the industry. Okay. Oh, yeah. And the last point down there. If you have really heavy doping, which makes them behave like metallic or gives them metallic properties, make them metal-like, then they are known as degenerate semiconductors or degenerated semiconductors. Degenerate or degenerated semiconductors. Okay. For the most part, the devices that we'll work with, they are somewhere in the middle of this table right here. Okay, so the diodes, the transistors, the FETs, the MOSFETs, everything that we use, they are in the middle of the table. Even I personally have never worked with a semiconductor, or I have not worked with a degenerate semiconductor. Yes. So it depends on the application. The question being asked is if you're creating fabricating a microchip, would you use a metal wire or would you dope with heavy, heavy profile? The answer is metal is widely used. So the chips that are fabricated, they all use metal. First, they used copper, then they use aluminum. Nowadays, it's a mix. Over the years, they've come up with many different materials that can be used and compatible with IC fabrication. There'll be some specific cases where you might want to use like a heavily doped semiconductor, but that would be only a specific use case for the simple reason that ion implantation or diffusion is not an easy process. It's an expensive process and needs to be tightly controlled. Okay. So once you have all these charge carriers in there, we are talking about charge carriers, right? So it's carrying charge. So when charge is carried or is moved, energy is being transferred, and we say that current is flowing in the circuit or current is flowing in the device. So in metals or in conductors, there's only one mechanism, which is drift. You apply an electric field, and the electrons in there are going to drift in response to that electric field. In semiconductors, there are two kinds of current flow. One is drift, the other one is diffusion. So drift is a response to an applied electric field. Okay, so you apply, in simple terms, you apply a voltage and the charge carriers will move in response to that external input. Okay, and so that can be easily described by Ohm's law. But there's a second kind of motion that occurs, and that's because of the doping profiles. Okay, the doping profiles are, if you're doping in a region, let's say this is the distance and this is the number of atoms of the doping profile. Closer, if this is the surface, you'd introduce your atoms into the surface, right? They're going to sink into a certain depth below the surface. So concentration, and this is exaggerated, concentration would be high closer to the surface, and then it starts to drop off, right? And once you go to a certain depth, charge carriers cannot penetrate beyond a certain depth, right? This laws of physics. So drift current is due to externally applied. Diffusion is because of the gradient in the actual dopant profile. Okay, so if you have doped a material with, let's say, 10 raised to 18 atoms per centimeter cube, there's a heavy concentration at one end. What the charge carriers do is they automatically diffuse the material in a bid to actually even out the charges throughout the entire material. Okay, again, if you have a heavy concentration of charge carriers at one end of the semiconductor material, So it creates a plethora of charges at one end, whereas the other end of the material or some other part of the material lacks all of these charges. Then these charge carriers will diffuse through the material in a bid to even out the charges throughout the semiconductor material. And that current flow is known as diffusion. Occurs because of the gradient that occurs in the doping profile. The gradient in the doping profile. Okay, and this is the applied voltage. Okay, so again, semiconductors, there are two kinds of current flow. One is drift, the other one is diffusion. And this effect, this diffusion effect, is going to be very critical when we get to the next topic, which is creating a p-n junction diode, a p-n or p-n semiconductor. Okay. Diffusion current, and this equation right here, this is also known as the Einstein's equation, kT over Q. It's also known as the thermal voltage VT. Thermal voltage VT. Because of thermal effects, there is a small amount of voltage that appears in the material that is known as the thermal voltage. It's given by kT over Q. T is the temperature in Kelvin. K is the constant. Q is a constant charge. Okay. All right. So now let's go back to this slide. So here, here we were talking about how when we introduce, or before we introduce any external dopants in our semiconductor material, there are intrinsically generated electrons. And every electron that breaks its bond leaves behind a hole, right? Electrons have negative charge, hole has positive charge. So a electron that leaves its spot and the hole that it leaves behind is known as an electron-hole pair. Okay, electron-hole pair. And that electron-hole pair is noted by Ni, intrinsically generated number of electrons. That Ni is equal to the number of electrons and equal to the number of holes. Okay. So again, Ni is equal to N is equal to P. Overall charge is always electrically neutral. It's always balanced out. And this process is known as generation. When an electron jumps back into its spot, that process is known as recombination, and the charges disappear. So early on, when researchers were working with these dopant impurities, they were introducing different materials into the semiconductor material. They observed an interesting phenomenon. It's like no matter how many dopant impurities they introduced in a semiconductor, the overall charge remained neutral. And so they were wondering, how can that be possible? If you're introducing 10⁻⁸ atoms, 10⁻⁸ donor atoms, let's say. So the number of electrons has now far surpassed the number of intrinsically generated electrons. So, what was going on? So they did, for, of course, decades of research, mathematical derivations. It turns out that there is that this phenomenon occurs that balances out the charge every single time. Doesn't matter how many dopant impurities you insert into your material. That law is known as the law of mass action. Pure mathematical terms, it basically states N times P, meaning the total number of electrons times the total number of electrons times the total number of holes is equal to Ni square, which we get from the above equation also, right? if Ni is equal to N, which is equal to P, and you multiply N times P, you get Ni square. But the law of mass action states that, not states, but it's derived, because even though it's not intrinsic anymore, we are introducing external dopant impurities in there, that law of mass action still remains true. So the law of mass action governs semiconductor physics. So what is exactly happening? Okay, let's talk about what's happening. Again, so this is a very important equation. N times P is equal to Ni square. Okay, total number of intrinsic generated carriers. So let's say we have a N-type material. We introduced 10⁻18 donor atoms in there. Every single one of them donates an electron. So now the number of electrons has increased, right? You have intrinsically generated electrons, you have intrinsically generated holes. Now you have an extrinsic number of electrons in there. So let's say intrinsic electrons were 10⁻10. Now your extrinsic electrons are 10⁻18. What happens is many of these electrons recombine with the holes that are present, and it takes out many of the positive charges. So as the externally introduced negative charges keep on increasing, the internal positive charges go on decreasing at the same rate. So the recombination rate increases to balance out the charge and make it electrically neutral. Okay, and I'll repeat again. As you introduce external charges into a semiconductor material, as you introduce external charges in a semiconductor material, the recombination rate increases to balance out those charges. And the equation that governs that is the law and the equation that governs it is the law of mass action. So this equation, Np is equal to Ni square, remains true for intrinsic semiconductor as well as doped extrinsic semiconductors. Okay, Np is Ni square. Yes. The number of charges? No. So the question being asked is, if we have a whole lot of electrons and a whole lot of holes at the same time, would it still not increase the charge? The answer is yes, it wouldn't increase the charge. Yes. So the recombination rate increases, meaning, so the question being asked is how does it actually work? So we talked about how electrons can combine with holes. So the process is known as recombination. When you recombine, one negative charge disappears and one positive charge disappears. Okay, so if it's an N-type material, for instance, and we introduce, sorry, not N-type. If we introduced a lot of donor atoms, it becomes an N-type material. There's a large number of electrons that are now available, but a big chunk, not big chunk. A lot of these electrons are going to recombine with the holes that are already present in that material. And so as the negative charges increase, the positive charges go on decreasing. And that rate remains the same. And that's a phenomenon that was observed early on. As the rate of recombination increases to balance out these charges. So let's say this is a balanced charge right here with my hands, and electrons and number of holes intrinsic. Now we introduce extrinsic electrons. Well, the number of holes, many of these electrons are going to recombine with these holes, and it's going to bring it down. And so these positive charges disappear. And a p-type material, the exact opposite happens. As the positive charges increase, the negative charges start reducing. But in both cases, the recombination rate keeps on going up until everything balances out. Okay, it's the recombination rate that balances it out. And generation and recombination, so natural phenomenon that keeps on occurring constantly. Okay, even if you take a piece of silicon, just leave it on your desk, there's always generation and recombination taking place all the time. Okay, that's been proven with, well, again, specialized area of study, solid state device physics. This equation is mathematically derived from the density of states and Fermi-Dirac equations. Yes. So, well, recombine is just electron jumping into an empty spot. It could be the same intrinsically generated carriers, or it could be the external electron. Doesn't really matter. Electrons would be the same, so it doesn't really matter which ones go into that spot. So you have holes that are generated intrinsically, or maybe due to some other acceptor atom that's present in there. But as soon as you introduce the other electrons in there and there are available spots in there, electrons are going to jump into those empty spots. And when it jumps into an empty spot, it's going to bring down the positive and the negative charges. Yes. That's a good question. So like if you have so many electrons that there are not enough holes, what happens then? Turns out that it is a fact that the number of electrons that we're talking about is still far less than what is already present in a material. Yeah, yeah. So there's always going to be enough number of spots to actually reduce those charges. So I'd love answering questions all day long, but we only have 13 minutes, so I want to get to that homework problem. So let's get to the homework problem. And let me do this. Which slide has a space? So I'll just do this. This one also has space a bit. All right, I'll do it here. So this is homework 1, and this was, I think, questions 1, 2, 3, right? So there is an equation that governs or that describes this charge neutrality, and it's known as the charge neutrality equation. And so that problem right off at the top stated the charge neutrality equation is given by, it gave you the equation. And so I'm going to write down the equation first. So the charge neutrality equation was, let's say CNE, just use the acronym. It was P plus ND minus N minus NA, always equal to 0. Now the book uses a subscript of O, okay, just to describe the density because it's per centimeter cube. So it's per volume, right? And when you have volume, it uses number of charge carriers, so it's charge density. So they are using a subscript of O, but this equation is still the same. Okay, in the book, it's PO and NO, which still means the same thing. Number of positive charges or holes plus the number of donor atoms will equal the number of electrons, negative charge, and the number of acceptor atoms. Hence, P plus ND minus N minus NA would always be equal to 0. So in an N-type material, NN, we already saw NN would be approximately equal to ND minus NA and P would be equal to Ni square divided by Nd minus Na. And P-type material, number of holes is approximately equal to Na minus Nd. And the number of electrons would be approximately equal to Ni square or Nd minus Na. Okay. Now, that's a charge neutrality equation, and the second equation that it states was the law of mass action, meaning N times P is equal to Ni square. So both those equations were given in that problem, right? So now, the problem itself at the top, question 1 asked you what type of material this was, because it had an excess of electrons, right? Nd was given as 0, and excess of holes. Nd was given as 0, Na was given as 10 raised to 17 or something, 10 raised to 17, right? So in that problem, if Na is greater than Nd, question 1 states what type of semiconductor? So the answer would be p-type. I think almost everyone got that correct. Okay. And then we can use the charge neutrality equation, plug in all of the values that are given to us. So now, if we take this equation, which is P minus N, so we want to plug, since this is a p-type equation, we want to plug this in there. Number of electrons in a p-type material, because we want to get rid of the minority carriers. So it's a p-type material. We want to get rid of the minority carriers. We want to get rid of N. So my equation now becomes P plus, this is 0, Nd was 0, minus, and this was N, the number of electrons. So this becomes Ni square divided by P. And then minus Na is equal to 0. So this is substitute Ni square equation. Okay. We are using this number of electrons as Ni square over the number of holes. Okay. Let's see. So Ni square over P minus Na. So now we have Ni square. We have Na given to us. We have only one unknown variable, that is P. So we can write P square minus Na times P minus Ni square is equal to 0. The value of Ni square was given. Value of Na is given. What kind of equation is this? Quadratic equation, one unknown variable. Solve for that variable, you'll get two answers. And b square minus 4ac is greater than 0, so there are two real roots. One is positive, the other one is negative. Obviously, the number of electrons or holes cannot be negative. And so there's only one possible answer. The answer is basically. And then once you have that number, you plug it into this equation to get the number of electrons. Ni square over P, and that gives you number of electrons. Yes. That's a good question. Yeah, so it turns out it's NP. Yes, that's what mathematically that it makes sense. Yeah. But did that make sense to everyone? Okay, you had the charge neutrality equation, and then we have the Ni squared is equal to NP equation, law of mass action. And then we just plug that into that equation. We obtain a quadratic equation, we solve it, and then that's the answer. Okay. And a few minutes left, so I want to go to the next problem, which was 4 through 6. In that, it was a N-type material. Number of donor atoms was higher than the number of acceptor atoms. But, so this is question 4 through 6. The answer for the first question, which is 4, is it's an N-type material. number of donor atoms was higher than the acceptor atoms. But unlike the first problem, in this case, the minority carriers, the Na was not equal to 0. The procedure is still exactly the same. You would still obtain a quadratic equation. The only thing is, instead of just taking Na is equal to 0, you plug in Na is equal to 10 raised to 17, which is the value that was given. And then you just solve it exactly as the first one. Okay. The homework is extended till tomorrow. You have multiple attempts to get it right. So if you did lose any points, if it was incorrect, hopefully now you have a better idea and understanding of what you need to do. If you still get stuck, if you have any questions, please let me know. All right. Be happy to clarify any doubts or concerns that you have. So we'll end class here today, and next class on Friday, we'll look at PN junction. So that's where our final semiconductor is, and then we'll begin the journey into diodes and then circuits.
Question: how you made the jump from going here to this?
All right,
Because
let's stop.
Oh,